Okay, so let's get started. So today I'm going to cover kind of the last few topics in control theory, and it's if you remember, I started out the course by saying they're going to sort of climb up to the top of the foothill, and then we can see the mountains. You know, from the plains you can't see the mountains. We're more or less at the top of the foothills now. At least we're not going to go any higher. And today you're just going to see the peaks of the mountains, you know, in the distance, and you'll get a sense of where they are, but you'll have no idea. I mean, you're not going to know how to climb them. Okay, for that you really need to take a course on control theory, an advanced course in control theory, or read a textbook in control theory, rather than a survey, which is really what we're at. Nevertheless, I hope that you have enough background, you know, in linear algebra and transforms and so on, so that you have some appreciation of what it is that we're trying to do in control theory. So, I mean, without this, you basically don't even know, you know, what these mountains are. What is it trying to do? So, so I guess I'm going to try and keep the discussion again at a somewhat intuitive level for these things, because it's advanced concepts. We can still learn from them some principles which are very useful in system design. So in particular the separation principle, which we'll talk about a bit more, and then the observability, controllability criteria for a system. And then I'll go on to digital control, and it's a paradox that even though computers are digital systems, computer networks are digital systems, they turn out to be easier to study as continuous time systems. So we've looked at continuous systems for the most part, but I'll just outline what happens in digital control. A proper mathematical treatment of digital control is complex, mainly because of problems introduced with aliasing and things like that, which I don't want to get into. So again, it's just a sketch. Okay, let me start here with state space analysis, which we started out last time, and I'm going to write down the standard equation for that. X dot equals AX plus BU plus FW, and Y equals CX plus DU. So this one is a single input, single output control system where Y is a scalar and X is a vector, U is a scalar. So we have single input. This is a single input over here. This is a single output over there. And the state is a vector. So this is actually we can allow the state to be a vector. And this is like a stepping stone to get to the multiple input, multiple output system. But we'll just start with this just for simplicity. And I want to first look at the notion of what happens when it's unforced. So when it's unforced, what happens is we're setting U equals 0. And we want to know, and again, we're going to study it in the absence of disturbances, just make it simpler. And so the idea here is that we've got the system at some initial state, okay, x0 is the initial state, and we are going to see what happens to the system when we stop giving it any more commands, any more input. Okay, just let it be and see what happens, okay. And what we expect to see in such a system is that because there's no more input, and if it is stable, is to basically we're going to see exponential decay of all the initial time constants, of all the initial system energy. So we have some initial energy in the system. We'll stop giving it any more input. It's just going to decay away if it's stable. If it's not stable, we're going to have some oscillatory or some kind of increasing amplitude. Okay, but if it's stable, we're going to see a decay. And once we go into the little bit into the mathematical formalism, you'll see how this comes out quite beautifully in the eigenvalue structure of the system, which is the eigenvalues of this matrix A, and you'll see it in just about 2 minutes. So it's really quite pretty. So let's look at the unforced behavior when U equals 0, W equals 0, and then at this point the system just becomes X dot equals AX, which we already saw in the when we did the analysis. And by analogy, last time I talked about this analogy to Y equals Y dot equals AY or CY. Okay, this has a solution YT equals some constant k e to the minus CT. So this, by analogy to this scalar equation, we can assume, we can predict that the equation is going to have solution x equals e to the at k. Okay, so what happens is that this a performs the role of this constant c, so it goes into the exponential like so. Okay, and where e to the at is a matrix exponential, and it's a shorthand, as you know. E to the at or e to the a is going to be I plus a square 2 factorial plus and so on. So it's an infinite sum. Okay, and this is where I stopped last time. Now, okay, and by substitution, when t equals 0, this gives us the fact that k equals x 0. This value k over here, this is going to be just the vector x at time 0. So the general solution is going to be x equals x 0 e to the a t. Okay, and that's the system over here. And so what we're saying is that the state space is going to be the initial vector x, whatever that x is, that is multiplying this e to the at. Okay, and e to the at, as we'll see in just a moment, is going to be a matrix of decaying exponentials. So x, the state, every element of the state is going to be decaying exponentials. Okay, if the poles are properly placed, if the system is stable, every element is going to decay exponentially, and that's just what you'd expect, right? Why is that? Let me actually give you the very simple explanation of this, and you'll see right away why it's exponential. Let's say that I take the number, I give you some value, let's say 5, okay, and let's say I'm going to multiply it at each time step by the value 0.8. So I'm going to 5 times 0.8 is going to become 4, then it's going to 3.2, then it's going to become whatever 32 times 8 is 2.56, etc. Right? So this sequence 5 to 4, 4 to 3.2, 3 to 2.56, etc. is what? We are taking the value, initial value 5, and we are multiplying each time by the same number, same fraction 0.8, which is less than 1. And so what you're going to get is a series of values which are going to go down like this, which is just a discrete exponential, right? It's a discrete exponential value decaying over time, right? So if you take any value which is positive and we multiply it at every time step by a number which is less than 1, we're going to see a decaying exponential, in this case a discrete decaying exponential, right? In the same way, if you take any initial system state over here, an element of x, so let's say x is equal to x1, x2, xn. If you take this value, it doesn't matter what it is, okay? It's a real system, so it's going to be positive energy, okay? Or let's just not worry about the energy right now, just assume it's positive for the moment. If I'm going to multiply it at each time step by some value less than 1, then it's going to decay. It's going to go down to 0 exponentially. That's why you see exponentials, because what we're saying is at each time step you're getting a proportional reduction. Why is it a proportional reduction? Because of this equation over here. X dot, the rate of change of x, is some fraction multiplying the current value. Right? All I'm saying is that I'm just going to take this thing and each time taking a fraction down. Right? It's just blindingly obvious that when you do that, you're going to get something that looks like this. So all this math over here, all this notation is just talking about a very, very simple system. I have a system where the rate of change depends on the current value, and it depends on the current value as a fraction. So if I have some value 10, it's going to go down to 8. If it's 4, it's going to go down to 3.2, etc. And that's all we're doing. It's basically all we're saying. Okay, and the whole theory here, all it's saying is that if we have such a system where the subsequent value depends on the past value as a proportion which is less than 1, then over time asymptotically it's going to go to 0. Well, you know, you can explain this as somebody in kindergarten, well, maybe grade 2 or something like that. It means if every step you go down proportionately, you're going to go down to 0. There's nothing so complicated about that. On the other hand, if each step you're going to inflate it a little bit more, it's going to go to infinity because there's no bound, right? That's all this is hiding over here. Behind this, all this math is really this very simple idea, because as you'll see in a minute, this is where it comes to. So let's explore that in just a moment. So here we have this equation, and let me put it in a box to say this is the one we're looking at. And we're saying, okay, here's this matrix exponential e to the at. What do I do with it? How do I find the inherent structure in it? And the way to do it is in one of two ways. So the first way is to basically evaluate e to the at as the actual exponential. And the way we do that is to diagonalize a. So if you remember, well, you may not remember, but well, first of all, what we want to do is that we want to look at this sum over here, 1 plus a squared by 2 factorial and so on. If A were diagonal, if A were a diagonal matrix, okay, of this form A11, A122, etc., then e to the a is really simple. E to the a is going to be nothing more than e to the A11, e to the A22, etc. So that's nice, okay? If a equals this, then e to the a equals that. So we've seen that before. So the question is, can we make A look like it's a diagonal matrix? And the answer is yes. Through the similarity transformation, we can do this. And I'm just going to sketch it over here. So what we do is we compute the eigenvalues of A. And let's say these are lambda 1 to lambda n. And for the moment, we'll assume they're distinct. Okay, they're distinct eigenvalues. And then they'll be corresponding to and the corresponding eigenvectors. Okay, x1, xn, or maybe I shouldn't call them x1 to xn, we call them v1 to vn. Okay, so that's the set of eigenvalues and eigenvectors. Then we know that a to the m, first of all, we know that D, we define D to be the matrix, the transpose. So it's going to be V1 transpose. So it's going to be V1 like this, the other vector V2, over here V3, etc. These are the vectors, the eigenvectors, and that creates this matrix D, which is the diagonalizing matrix. Okay, and X equals this. And then we see that, and D is going to be the diagonal matrix lambda 1 to lambda n. So the matrix, diagonal matrix of the eigenvalues of A is going to be this vector D, and then we can just say A to the m is going to be equal to X D to the m X inverse. And now this, by the way, is straight out of the linear algebra stuff that we saw earlier. So I'm just repeating it to remind you, so there's nothing new here. So we know what X is, because we know if you compute the eigenvalues and eigenvectors, we know what X is. We know what D is, because that's just the eigenvector. This comes from the eigenvectors, that comes from the eigenvalues. So we know what A to the m is. If you know what A to the m is, then we can actually compute each of these elements. And actually, and I'm not going to go into this, it's pretty straightforward to compute e to the at, where A has been diagonalized, because you can replace A by x d x inverse, okay? And there's a little bit more that goes with it, but it's not super hard to do this. And so if we can diagonalize A, which means if A has distinct eigenvalues, then we can easily compute the matrix exponential. And at this point, we are basically got the complete solution over here, because now this matrix exponential turns out to be a matrix we can evaluate. Okay, we can tell you this is exactly what it looks like. And for the specific case where A happens to be diagonal, what we're going to see is that this matrix exponential over here is going to be just this values over here. Okay, and as long as these A, these values over here, what are these? This is just the eigenvalues of A, right? If A is diagonal, the diagonal elements are the eigenvalues of A. If these diagonal elements are going to be less than 0, then these are going to be negative exponentials, e to the a something, and these are going to multiply the corresponding terms of x, and which means that each value of x is going to decay at the rate e to the aii, which is in fact the eigenvalues of A. So you can see intuitively what's going on. We are saying that if A is diagonal, the system is decoupled. the elements they don't interact with each other because we have no cross elements over here. Each element in the state is doing its own thing, okay? And what is it doing? Well, it's going to be decaying at the rate corresponding to the essentially the diagonal values of A. Now, if A is not diagonal, we're going to have to do some little bit of work to use D instead. So D is the diagonal value over here. And it will turn out, and I'm not going to explain it here, it will turn out that if these lambda I 1 to lambda n are going to be all in the left half plane, they're all going to be negative values, in this case the real values, it's going to be, it's going to have the system is going to basically decay nicely. So you have some initial energy state, and every element of the state is going to decay down to 0 asymptotically, okay, at an exponential rate. Okay, so you see what's going on? So all this is basically the same intuition. You have some value, and you're going to proportionately reduce it, and that's what the structure of the system is going to be. Okay, and it's because it's a linear system. It's a linear time invariant system. That's what giving us all this beautiful insight. If it were time varying or if it were non-linear, then we can't use this analysis over here. So I'm basically just sketching something over here, and it gets a bit more complex. How do you account for e to the x and e to the x inverse, and so on. So anyway, we're not going to put it there. If A is not diagonalizable, if A doesn't have distinct eigenvalues, then the best we can do is to put it in what's called Jordan canonical form, where we're going to have these values over here, plus we're going to have one additional row above it, one additional diagonal above it, which could have non-zero elements, and then the rest are all going to be 0, and this is called the Jordan canonical form. And when you have the Jordan canonical form, you can still compute the matrix exponential, but it's a bit harder. And so, again, I'm not going to show you how that's done, but suffice it to say that this has been well studied. Very many techniques exist for it. So no matter what A is, we can either numerically or analytically compute either the diagonal form or the Jordan form, and use it to compute A to the m and also e to the AT. And so this is how we kind of proceed when we do state space analysis in the time domain. Okay, state space analysis in the time domain for SISO LTI systems. So remember, we still got it as SISO because y is still going to be a scalar here. So it's SISO LTI under those conditions, and in the time domain, this is what you're going to get. Okay. So any questions about this so far? Okay. And again, it's unforced, so we're putting all these conditions. Yes? Yes. Yes, it's a good point. So the question is, since the choice of state variables is it's not arbitrary, but it's a design choice, right? Can we choose the state variables in a way where A is diagonal? The answer is yes. Okay, when given a particular state, we always want to choose the state variables such that the evolution of the state variables is decoupled as much as possible. Intuitively, we want to pick orthogonal state variables. Okay. Because what the diagonalization is doing actually is to create an orthonormal basis to the existing basis. If you think about it, we're taking this basis space and we're rotating it to find another basis space, which is actually this basis space to the eigenvectors from a basis space for that vector space, right? So we're going to take some existing basis space and do essentially a multidimensional rotation. It's called orthonormal transformation, and that creates a new basis space where all the vectors are actually going to continue to be orthonormal, and the state elements are going to be actually then completely decoupled from each other. They're all expressed as linear multiples of the orthonormal basis functions, right? So we get complete separation of the basis vectors. Okay, so that's the idea that we choose. So diagonalization or the similarity transformation is an eigenvalue preserving transformation into a new basis space where the state vectors turn out to be decoupled. We have essentially no cross coupling in the A matrix. That's really what's going on. So the D matrix is a decoupled matrix. Okay, so if that didn't make sense, it's okay. It's a bit more advanced. But the point I want to make is that if you want to choose a system and you want to choose what the state variables are, try to pick state variables that are going to be independent of each other. Because they're independent of each other, these cross terms will go away, and then you'll get a very clean, simple e to the at, and then life is really simple. Yes?
Yes, because something else is important when using states. It's like states must be the way that you have measured them.
I'm going to come to that. So the question is, what are the other constraints on the states? Do we need to be measuring them and so on? And we talk about observability and controllability. I'll talk about that. So we're not there yet. Okay. For now, we're just going to focus on making them easy to process using e to the at. All right, let me continue here with this. Right, so this e to the at, let's come back over here. This e to the at over here is, if you just call this, this matrix as B of t, okay, just to show you, just a matrix that's a function of time, is converting the x0 to x of t, because x is a function of time, and so we call this the state transition matrix. Okay, you've seen the word state transition matrix before. In the case of stochastic matrices, it's the probability when you go from one state to another. That is a state transition matrix in the sense of queuing theory. Over here, this is called the state transition matrix in the sense of control theory. So the same phrase is reused. Just wanted to point that out. Okay, now let me come back to this question where we are. The first thing that happens is going to come to e to the at, and you say, okay, e to the at is, if you diagonalize it, etc., we get something. There's another way of doing this, which is to use the Laplace transform. So just like we can avoid convolution by doing Laplace, we can also avoid computing this using Laplace in the following way. So you can take the Laplace transform of this box over here on both sides to get Sxs minus x of 0 equals Axs. And so if we move this over, we get x of s equals Si minus A inverse x naught. Okay, and so xt in the time domain therefore becomes the Laplace inverse, the inverse Laplace transform of Si minus A, another inverse over here, x0. So nice, compact, pretty, but incomprehensible. I mean, what's going on here, right? So we have to basically compute the inverse of this matrix Si minus A, and then compute the inverse Laplace transform of that, and then multiply the x0. So this actually is nothing more than e to the at. Okay, if you compare this with that, it's the same thing. All we're saying is, instead of computing the matrix exponential in this form, it might be simpler in some cases to actually compute this matrix Si minus A, find its inverse, and take the inverse Laplace, and that's an alternative way of getting it. And again, it turns out in some cases it is easier to do it, but not always. So we're just giving two approaches. Okay, and again, if A is diagonal, you'll see that this turns out to be actually pretty straightforward, because Si minus A is going to be diagonal as well, right? And then what's going to happen is the inverse Laplace of that is of a element I minus A is going to be what? It's one is going to be just 1 over e to the minus e to the A. Right? So this one, if it's A is diagonal, this looks like basically S minus A 1 1, S minus A 2 2, etc. S minus A n n. And if you take the inverse Laplace, is going to be you have to find the inverse of this. When you find the inverse of this, that's going to go like that. And then when you take the inverse Laplace, it's going to go to e to the A11, actually. E to the A22, e to the ANN. So in fact, this computes the same exact thing in a slightly different way if you do it, if A is diagonal. Again, if you have orthogonal space elements, this is pretty straightforward to see over here, okay? And all you need to know is that the inverse of a diagonal matrix is the inverse of each of its elements, and that's actually pretty straightforward to see, because you want to multiply this by the diagonal matrix to get ones, right? So obviously each element has got to be an inverse. So this works out. Okay, that's sort of a sketch of what we do for the unforced case. Okay, are there any questions about this over here? Okay, so let me move on to the forced case where it's actually even less detail, if that's possible. And I'm just going to give you the time evolution, not the in the evolution of the time domain, the equation for that, and explain what it's doing. And then we'll go straight into the other. So here, the result, and just going to be the result, is that xt is given by e to the at x0, x0. So this is obviously your unforced response. That's what we already saw. Plus, we're going to get essentially a convolution from 0 to t, and this is because it's causal e to the a t minus tau bu tau d tau. Okay, so this is the force part. And what we're saying is that the output is going to be the convolution of this e to the a term, e to the a t minus tau term, with this other term bu. Okay, so b is constant, so use the command. So this is your control. This is a constant, and this is sort of this represents sort of the system. Okay, what we've been calling G. Okay, the system G is basically represented by x dot equals ax, and so e to the at minus tau is roughly corresponding to what we've been calling the system in control theory, the G part. And so what we're saying is that the actual output depends on whatever happened because of the initial system condition. And if x0 is 0, this goes away, right? If you start the system in equilibrium, this basically goes away because x0 is 0, but maybe it's not 0, maybe it's something else. Plus, we're going to have something convolution which has part of it what the system is doing, e to the at minus tau, convolved with what the command is doing, which is bu tau. Okay? And so this opens the possibility that if we want to control xt, which is the state space, and from xt we want to control y, because y, it depends on x through this equation over here. So since y is some function of x, and of course u, it's possible to choose a u over here such that the y is where we want it to be. That's the whole goal over here, to choose the u such that the y is the right way, and that's of course the standard control goal. Now, this time domain system is again fairly complex to analyze, and so I'm going to now go into two criteria, okay, of how we study the system, and then come back to solving this, but we'll do it actually in the Laplace domain rather than the time domain. Okay, and so let me first give you the criteria, and then I'll talk about the how to do it. So this is the forced response. It's really not a whole lot to this other than what you'd expect. The output depends on the initial condition and the system, and it depends on the command. Okay, so let's look at these two criteria, observability and controllability. And I'm going to erase this over here. And okay, I just need that. So okay. So let's look at observability over here. Okay, so we have a system in which we have some internal states, okay? And so far, we really haven't said anything about what these internal states are, or can we observe them, or anything about them, right? So it turns out that when we're doing state space analysis, these two criteria are supremely important: observability, controllability. Observability essentially says, by looking at the output of the system, I can figure out what the initial state was, okay? And I'll define it more precisely in a moment. And controllability basically says that I can get the system to go from any initial state to, or I should say, from the, or more precisely, I can go from the initial state of equilibrium, x0 equals 0, to any state I want to get it to, okay, by choosing some command input. Okay, so if the system is observable and controllable, then we can actually always design a controller for it which is stable and achieves the desired control goal, whatever the control goal is. Okay, so it's a sufficient but not necessary condition. Okay, in the sense that I can look at a system and say, okay, is it observable? Great. If it's controllable, yes. Okay, I know what to do. If it's not observable, then I have to be. It may still be. I may still be able to get to where I want to get to, but it's going to take me more work, and I'll explain what that work is just in a moment. But it's a good thing to check, because if the system is observable and it is controllable, then life is good. We can just go ahead and just use a standard controller for it. Okay, otherwise you have to do some extra work. Okay, so these are like a checklist. Can I take a system and say, is it observable? Is it controllable? So let's start with what we mean by observability. Okay, if knowing. Okay, let me call this system over here. Okay, the state equations. These are the state update equations. So let me call that S. Okay, so if knowing S, okay, output Y and the input U over the interval or the finite interval 0t, okay, allows us to determine x0, then S is observable. That's the definition. So what we have is we know the equations, okay, somehow, and we know we're given it some input. We control what the input is. It could be a step input. It could be anything we want, and we observe the output. And you say for some duration, it's at the end of it, I know exactly what x0 was. I know what the initial state was. If I can do that, then it's observable. That's the definition. Okay, and if okay, so the equivalent condition. The equivalent condition is a bit two equivalent conditions actually. One is that this matrix C. CA squared. C is basically the row. It's a row vector. Okay, it's this vector over here. Y equals Cx, because remember C is a row vector, X is a column vector, and Y is a scalar. We're still studying SISO systems. So C is a row vector. CA is going to be a row vector as well. CA squared, etc. CA to the n minus 1. If this has rank n. Okay, so now it gets even easier. So this is a kind of abstract condition. You kind of say, well, what does it mean? It turns out that this can be equivalently expressed in this way, which is now a mechanical condition. We take the state equation over here, we plug it in over here and say, okay, what is the rank? We just do Gaussian elimination. We find out whether they get any inconsistencies, etc. If we do, we know it's not got rank n. If it's full rank, great, we are done. If it's full rank, we can just easily say that it is observable. And there's an even easier condition. If A has equivalent condition A, I should call it 1. The other equivalent condition is that if A has distinct eigenvalues, and distinct eigenvalues, as you'll see, is always a nice thing to have, distinct eigenvalues, then let P be a non-singular. It's a diagonalizing matrix. So that's the same as that X over here that we had earlier, which is this is the matrix such that P inverse A P equals as a diagonal. That's the definition of a diagonalizing matrix. Then all we need to check is to see that CP has no zero columns. If CP has no zero columns, then it's observable. So again, this is easy. So what we do is we take the matrix, we stick it into a solver and say, okay, what are the eigenvalues? Finds eigenvalues for us. We hope they're distinct. Keep your fingers crossed, hope they're distinct. If they're distinct, then we say, okay, what's the diagonalizing matrix. Again, that's easy to find, and you just check CP has no 0 columns. So in a typical control system software,